It's now my pleasure to introduce today's keynote speaker, Dr. Gary Patton, Corporate Vice President and General Manager of Design Enablement Group in Technology Development for the Intel Corporation.
It's very exciting to be here today to talk to you about how we're going to keep Moore's Law alive by moving from system on a chip to system of chips. And I'll talk about the 5 enablers for getting there. And one key one is for us in the foundry business to move from being a silicon foundry to being a system foundry. And I'll talk about what that means. We all know that the demand for compute and storage is just going through the roof. A couple examples here. The world creates today 270,000 petabytes of data every day. That's over 10 to the 20 bytes. That's huge. And it's predicted that in 2030, each individual on average will have 1 petabyte of compute and 1 petabyte of data, less than 1 millisecond away to access. To get there requires continued innovation. We're going to continue to be pushed to innovate and evolve so that we can support this continued growth. And we have a long history in this industry of innovation. Think about it. What other industry has had such a profound effect on the world and how everybody lives their life? Think back about 40 years. I remember when the IBM announced the portable PC computer, weighing a dainty 30 pounds and having 256 kilobytes of memory. Oh, you could upgrade it to 640 kilobytes. That's a long way from the petabytes that I'm talking about here. Think back about 40 years ago. The remote key fob became a feature that went with automobiles. Today, we have autonomous cars. In fact, I've ridden in the Waymo. It's a lot of fun. And by the way, you don't have to tip the driver. He doesn't get upset if you don't tip him. And then 40 years ago, technology was really for people who had a lot of money. Today, we've driven down the cost to where it is pervasive in the world. The challenges of continuing AI, scale. Today, the demand for chips is growing substantially. We shipped 1.7x more chips this last year supporting AI, but the demand was growing even faster at 2x. And roughly every 10 months, doubling the amount of large machine learning compute requirements. Huge growth. At the same time, energy efficiency is becoming a big challenge to support AI. If you look here in this example, it's predicted that AI will drive almost 100 terawatts hours per year. That's equivalent to what some countries use in energy in a year. Now, there's opportunities to improve that. We're only using about 30% of the compute capacity, but it's going to require a lot more than that to be able to evolve. And that's getting to this innovation, which I talked about, which is a system of chips. This is the graph. This graph on the left came from Art de Gius from Synopsys, and he talks about some of the challenges that we're facing as we go forward. Scaling is slowing down. We're not getting the same density power performance improvements that we did in the past. Second, conventional architectures like von Neumann are also slowing down. We're reaching memory bandwidth and latency issues, and we're seeing challenges in terms of thermal. So a lot of headwinds, right? So what he proposes is, hey, we can evolve. Let's figure out how we integrate and optimize between packaging and silicon to go to something he coined called SysMore. But have no fear, we faced walls before. This is not the first time. This is a chart I used from a talk over a decade ago at SEME ISS, and it provides a little bit of historical perspective. We've hit walls many times in our history. The gate oxide limit, for example, planar device limit. Each of those times we could have said, it's game over, we're done, technology scaling has ended. But no, we innovated. We figured out ways that we could get past those walls, and we'll do it again here in 3D. You'll see 3D listed here in the middle, just to the right of the dotted line. I was a little bit optimistic on when 3D would come in, but it's here now. And what's driving it? I talked about 5 enablers. The first is there has been tremendous innovation in packaging. And it's highlighted here some examples from Intel, starting with standard packaging on the left, the evolution of 2.5 and 3D packaging solutions such as EMIB, which we had announcements around yesterday, Foveros Direct, which involves direct hybrid bonding. These innovations are driving a 10,000 increase in interconnect density and a 50x increase in energy efficiency. That's huge. That's huge in terms of enabling this system of chips. Second key enabler is getting to an industry standard for interconnect between chips. And in particular here, Universal Chiplet Interconnect Express, UCIe. This allows you to mix and match chips from different technologies and from different foundries, and they'll all connect up and work together and have incredible bandwidth and latency. That means that you don't necessarily have to also replace every chip with every generation of your product. You can focus on upgrading the chip where you get the best ROI. So a lot of flexibility in how you design this. And since you're dealing with a system of chips, you're not limited by the reticle size for silicon lithography, because you can go to many times that in this solution. The third enabler, and in that case, this is here today. This was launched a little over 2 years ago with 10 companies. There's now 135 companies that are part of this UCIe Standard Express, and this will really revolutionize the ability to do systems of chips. And the benefits are shown on the graphs here. On the bottom right, you can see bandwidth density divided by over 1 over bump pitch. UCIe 1.0, which is for 2.5D, gets about a 1 to 2x improvement in bandwidth. UCIe 3D will get another 2 orders of magnitude. So a total of 3 to 4 orders of magnitude improvement in going to 3D in bandwidth. On the left is energy efficiency. UCIe 1.0 gives about a 1 order of magnitude improvement in energy efficiency, another 1 order of magnitude when you go to UCIe 3D, for a total of 2 orders of magnitude improvement. The third enabler is system technology co-optimization. Let's not just optimize the silicon and the packaging and software architecture independently. Let's optimize them as a complete package to really get the maximum power, performance, and area. I show here a more detailed view of that system technology co-optimization. On the left is the traditional design technology co-optimization that we've been doing for the last two decades, where we work closely between design and process to figure out how do we squeeze every bit out of power, performance, and area, PPA. When it was first introduced about two decades ago, it gave a very small improvement in power, performance, and area. Today, we literally double the power, performance, and area of the technology through this DTCO function. On the right is optimization of the packaging, optimization of the chiplet design, validation, and the packaging technology itself. And we could do those independently, but the real power is in putting those together and optimizing them together along with the system architecture and the silicon validation. I believe that we're kind of at the same point we were on DTCO 20 years ago. We're at the beginning here on STCO, and we'll see some improvements from this co-optimization. But over the next 2 decades, I believe we'll get more than 2x in performance improvement out of optimizing this system technology co-optimization. So Moore's Law is not ended. We will continue to innovate in silicon. We'll continue to innovate in packaging. We'll continue to innovate with our ecosystem of EDA and IP providers to deliver the most out of the basic silicon and packaging technologies. But we're going to combine that with system innovation. So innovation around memory and interconnects, system architecture, software and firmware, and optimize that whole thing as a combined package. The third key element of enablement is going from being a silicon foundry to being a systems foundry. So enabling these system solutions and this system technology co-optimization. And it starts at the very bottom. The foundation is being a world-class foundry. And I highlight our key foundry offerings: Intel 16, Intel 3, which are in manufacturing, and Intel 18A, which will be in manufacturing shortly. And then we defined at our Intel Connect event earlier this year our roadmap to go back to a 2-year cadence of technologies, with the next one being Intel 14A. The second layer is ensuring that you have a resilient supply of both silicon and packaging. That means a global manufacturing footprint, and that means having high security in those offerings. And then the third are the elements to enable that system capability. So the advanced packaging that I talked about, the UCIe to allow interconnect, high-speed interconnect between these various chips in a way that allows you, again, to mix and match chips from different technologies and from different foundries, and then optimization of the software on top of that. So where are we on this? We started on the left with 2D type packaging solutions, where it's really a system on a chip, to today where we're talking about going to systems of chips. And I highlight the two examples that we have for 2.5 and 3D in Intel, EMIB and Foveros. So if you look at where we are, if you look on the left, we have invested in Intel very heavily in this capability. We have today 2x the wafer level industry capacity, and we have 3x the 2.5D advanced capability. We are putting the capacity in place to ensure that we can meet the growing demand for AI and for high performance computing as we go forward. And you can see with the graph, we're continuing to invest because we're expecting that's going to grow significantly over the next decade. In the middle shows the type of solutions that we have in manufacturing today. We have over 100 2.5D designs that are in manufacturing. The graph here shows the number of die in a package versus the area of the package. We have solutions that are in manufacturing today that have almost 50 chips in a package. That's a real system of chips, I would say. And we have as much area in some of these solutions that are approaching 10,000 square millimeters. We have all of the key capabilities. These are what you need to be able to enable this kind of system foundry, design and packaging architecture capabilities, including power delivery, how to design power delivery, how to deal with thermals, advanced packaging technologies, which I talked about, ensuring a supply of FPGA substrates, assembly equipment and test, and then that system technology co-optimization methodology that I talked about. This highlights some of the offerings that we have in this space to support this system of chips. On the left is the traditional 2D FCBGAs, extending out to 2.5 and 3D. EMIB 2.5D, which has been in manufacturing actually since 2017. So there's almost 7 years of experience manufacturing. EMIB is UCIe compatible, and it can support greater than 7x the reticle size in terms of silicon in a package. Foveros, also in manufacturing. This one in manufacturing for almost 5 years. Again, UCIe compatible, very important for that mix and match that I talked about. And that can support over 4x the reticle size equivalent of silicon in a package. And then we have EMIB 3.5D, which combines EMIB 2.5D and Foveros for a real integrated solution. And then on the right is Foveros Direct 3D, which has direct copper bonding. It gives the highest density and lowest resistance die-to-die interconnects with a power performance per bit of about 0.05 picojoules per bit. Pretty low. This highlights the differentiation, the elements that need to go into this system of chips. Very large form factor packages, 120 by 120 square millimeters with multi-layer design. Focus on silicon package board co-design. The elements of high-speed interconnect between the chips. These interconnects of Foveros and EMIB, which I talked about previously. And of course, you have to deal with cooling, and you got to be able to test it. Those are all the key elements that go into this system of chips. You also have to deliver a complete power delivery solution to be a system foundry. On the left is our Intel 18A technology, which has PowerVia and ribbon FET. The PowerVia, which delivers backside power as well as backside clocking, dramatically reduces the IR drop by as much as 30% and improves Fmax by 6%. Then for dealing with inductive power supply droop, if the chips are manufactured within Intel, in that 18A technology, we have a very high density MIM technology, which is 400 femtofarads per square micron, 5x the amount of capacitance. If you're delivering to us a chip to our packaging, which is from outside of Intel, we also have solutions for that, which is thick core combined with MIM in our EMIB technology, to add capacitance to deal with that inductive power supply droop. So we have many options here to help with that particular issue. The fourth key enabler is design enablement. So in Intel, there wasn't a focus, frankly speaking, until 2019. The technology group had three very technology-oriented pillars: research, logic technology, and packaging technology. But in 2019, we formed the design enablement group, recognizing for design customers, this is as important as the technology in being able to get design to market fast and fully leverage the technology. Not having good design enablement technology is like having a race car, but without racing tires. You're not going to get very far, and you're not going to get very fast. So we've invested heavily over the last 5 years in getting ready for foundry and getting ready for system foundry. We doubled the size of the design enablement organization, adding significant number of people who had foundry industry experience to augment the very good people that we already had. Second was aligning to the industry in terms of methodologies. So getting away from our homegrown Intel tools, getting to industry standard tools that you are used to using and expect to use if you're going to design in our technology. And we broadened our EDA tool offerings, and I'll talk about that more in a minute, but we've tripled the number of EDA tools that we enable on our technologies. Getting to silicon-based maturity criteria, so that's PDKs that are defined by where the silicon hardware is in terms of defect density, in terms of performance, in terms of CP/CPK. This is very important for you to know where we are in terms of the maturity of the technology, so you know that we're stable and we're ready for you to design in our technology. And last, design ease of use. Intel had a reputation, I knew that prior to coming, as not being the easiest to design in. And we put tremendous investment, especially in our 18A technology, in getting to very competitive design ease of use so that you can design easily in our technology. Third, another thing that Intel was not known for being a very open and collaborative company. We've changed that completely. We partner very deeply with our equipment suppliers now. We partner very deeply with our EDA partners. I have multiple reviews every week where we share and exchange learning between us and our EDA partners. We become very open with our customers, and our focus is we want to leverage all the industry learning that's out there so that we can accelerate our readiness for technology and design. Fourth is quality first culture, and that's not a slogan. We built a QA organization, we built and refined QA methodologies so we could have very high quality PDKs and very high quality foundational IPs. And we've partnered with our EDA partners to improve their methodologies. We did something that Intel would never have done 5 years ago. We actually contracted one of our EDA suppliers to audit our run sets. They gave us some great feedback on how we can improve it and get more aligned to industry, and we implemented the changes that they recommended. And then last, we recognize that this is a service business, and we need very strong customer focus and customer support. So we built up a customer support organization for design enablement, brought in quite a number of people who had foundry experience and experience in customer support in foundry, and we actually did some innovations. Many of you may know about design rule manuals. They've been for many years PDF documents that you have to thumb through. Very painful if you're trying to learn a new technology. We built a web-based system which allows you to go into your design, click on where you've got an error, for example, and will take you right to that part of the design manual. So very quick to understand where your design issues are and diagnose them and figure out how to fix them. So innovation in customer support and design ease of use. I mentioned we broadened our EDA tools support solutions. This shows the various EDA tools that go into a PDK: circuit simulation, custom layout, APR, fill, extraction, physical verification, a number of different reliability type tools, and the various tools, EDA tools that are in each of those categories. You can see from the green dots, we really only supported back in 2020 a small subset of the tools that were available in the industry. But we recognize that we don't get to dictate to our customers what tools they use. If we want their business, we have to enable the tools that they're used to using. So we had a massive effort over 3 years. We have now completed at the end of last year enablement of all of these key tools on Intel 16, Intel 3, and Intel 18A. And we're getting ahead of ourselves on 14A. We've already enabled quite a number of tools on our 14A technology, and by the end of this year, we'll have completed the enablement of all of these EDA tools, which is a year ahead of what we did on 18A. And we're not limiting that just to this 2D solutions. We're also focused on enabling this, partnering with our EDA suppliers on 3D IC and advanced packaging. And I show a table on the right, again showing the various tool domains that go into 3D for both EMIB and Foveros. And you can see most of the tools are already enabled for both of those technologies. And over the next couple quarters, we'll complete the remaining ones to have a full suite of tools for both EMIB and Foveros. Very important for being a system foundry. A key part I mentioned was partnering with our EDA suppliers to basically, in a number of key areas. First is that DTCO, Design Technology Co-Optimization, early in the pathfinding stage. So we engage very heavily with both our partner Synopsys and our partner Cadence to squeeze out as much power, performance, and area out of the definition of the technology on 14A as possible before it would enter the development phase. We've also partnered with our EDA suppliers on how to build the right EDA tooling for these new capabilities, such as PowerVia, for example, which do require new types of EDA tool capabilities and can deliver significant improvements in power, performance, and area. In the heat map that you see on the top, red indicates very dense designs, high utilization, green is less dense. And you can see with PowerVia, we can get a 10% reduction in area, and you can see the increase in red and the decrease in green, indicating the higher utilization that we achieve. Also, PowerVia delivers about a 30% improvement in IR drop, and that's a result of the capacitance improvements that you get with PowerVia. And then frequency, about a 6% improvement as a result of the reduced capacitance. We're also partnering with our EDA suppliers on our 3D IC technology, and you may have seen the announcements that we did with our EDA partners around our EMIB technology yesterday. Very important in enabling the DRC and LVS requirements with TSVs, and also developing a complete design flow around 3D IC, which I'll talk about in a moment. So this shows a 3D IC design flow and the various capabilities that are needed to do 3D IC design. I would call the bottom four, implementation, extraction, reliability, verification, sign-off, as I would say evolutionary improvements. Taking what we've done on 2D and enabling them to handle the constructs like TSVs that come in a 3D solution. The top I would call revolutionary. This is understanding in a 3DI system, how do you partition the design to get the best performance, power, and area? How do you floor plan it? How do you do the power gridding, and how do you deal with the thermal constraints? And then we have these capabilities in place today, but they're early. They still need continued work, and we need support from our EDA partners to continue to refine these tools and improve them so we can get the best out of system of chips. I start here with the revolutionary part. So we need continued focus on tool and flow capabilities to enable this design partitioning across tiles of different design. I mentioned that. And then the early design decisions are needed to incorporate thermal constraints based on what data we have to understand the thermal considerations. And then finally, the capabilities for that co-design and improving that so we're really squeezing as much out of the system technology co-optimization that we can. And then here's the evolutionary part that I talked about. So we have these capabilities, but keep in mind, the 2D solutions were refined and improved over many, many years. We're at the early stages for 3D, and so there's continued work needed to make them as best as they can to help you with your designs. So for example, physical design implementation, tools needed to significantly enhance natively handling multiple variants of TSV that may come with the different kinds of chips that you'll have in the design. Being able to model and manage thermomechanical stresses in these complex systems of chips in the design flow. And then the ability to perform static timing analysis on synchronous data paths across multiple dies without an explosion in the number of sign-off corners that are required. So now if you put it all together, we've got the design methodology flow on the left, which I just talked about, the PDKs, which are now enabled for both 2D and 3D solutions. Advanced packaging solutions, which I talked about. Foundational IP that covers both 2D and 3D. And then a very strong EDA ecosystem and collaboration. Wrapped around that is the system technology co-optimization methodology so that you're getting the best power, performance, and area out of the technology. You put that all together, and we call that a 3D system design kit, or 3DK, D being for dimension and for design. So, in summary, if I wrap it up, I hope I've convinced you that system foundry and this system of chips, it's not a future thing, it's today. Thank you very much.